Hello students, last class we started the numerical on muff coupling or sleeve coupling. It's a very simple type of coupling. So we finished almost 3 steps. I think 3 steps for design of sleeve coupling. So we've decided on diameter of shaft. Then based on the diameter of shaft, we have decided on the diameter of sleeve, and we also checked that sleeve whether it is coming within our limits, within the safety limits or not, and we saw that it is within the safe limits. So now let's move on to the next part, that is the fifth step, the fourth step. So the fourth step, just put it in the activity. This is the check for sleeve. So the last step here is to just know uh, to see the design of key. Okay, what is the design criteria which is to be followed, and we'll just check whatever dimensions based on the whatever table we have. So this is the table we have 17.4. So depending on diameter of shaft, we just take the dimensions and then substitute that and see whether it is within the limits or not. So that's our goal. So these sleeve couplings, they always embed the jib head key. That's why we are referring to only the jib head keys. So let's start off with this step. So design of key is the fourth step. So step 4 is design of key. So you need to design this key. So this is based on the sequence of equations. So from table 17.4, okay, from table 17.4, and for diameter, this diameter of shaft D equals. So what diameter we got is there is a diameter of shaft 40 mm. So 40 mm is the diameter of shaft. So what we need to do is refer to this table 17.4 and extract the dimensions of key. Okay, let's check it out here. So this is 17.4, and you can see here for diameter 40. Up above is given above. Let's refer to this above, and it is above this value 38. So above 38, okay, you are supposed to take this value, these values here, up to 44. So this is the limits. So 38 to 44, we take B as 12. So this is our B and this is our H. So 12 and 8. So that's how we take the dimensions. 12 and 8, right? So B is 12, H is 8. So we are deciding the dimensions of key. So this is 12 mm. Height is 8 mm. This is 8 mm. The length, no, length will be as usual. So the length of the shaft itself. So length of shaft was 140 mm, right? So this is length of sleeve 140. So we'll take this as also as 140 mm. So 8, 12, and 140. So 3 is the width. We got 12 mm from table. Similarly, H we got 8 mm from that table 17. Right. So only the length 140 mm. So that will be as we did the previous one. That is the sleeve length itself. So jib head will come after this dimension. Not much worried about it. Now we need to check whether these dimensions are suitable for the given stress values. The stress values were given here. The data for shaft, these were the two stress values, that is 60 and 130. So let me just copy this. Okay, so these both are the limits. We need to check whether they are falling within this range or not. Okay, so for that we use the formula width of key given by B equals 2 times the torque divided by tau d L into T. So this is according to equation 19.50. Okay, that's according to this equation here. And now what we need to do is 12 is already fixed. Okay, we just need to check whether it will carry this much load or not. Okay, so keeping tau d as unknown, find substitute all other values. Okay, so B is 12 equals 2 into empty. We know it already. 477.5 into 10 power 3. 477.5 into 10 power 3 divided by D. L. L is 140, same as the length of sleeve, and T is 40 mm, the diameter of shaft. So being tau d as the unknown, that is this limits. These are allowable stresses. So we just need to check whether it is coming in the allowable limits or not. So tau d equals, we'll get some value. Just find out what value is. Let's see. 2 into 477.5 3 divided by 140 into 40. So you can calculate parallelly along with me. Not audible. Am I audible? Okay, so we have the tau d value. We need to extract that. So what I've got from the calculation is I've got 14.21 newtons per mm. So this value of tau d is, we check here, it is less than that. 60 is what we have. So this is less than 60 Newton per mm square. So therefore, according to this width of the key, or which is telling us the shearing stress, it is safe. So, but let's not conclude yet. Let's find for the thickness of key formula. Use the thickness of key formula and find out whether it is coming under the crushing stress. So let's say thickness of key. So this is just to find another parameter, that is whether it is falling in the limits of crushing, whether it is failing under the crushing loads or something like that. So this divided by sigma b, that is crushing, L d. This is equation 19.51 according to data handbook. Again, keep everything substituted only except sigma b. We just need to check whether it is falling below this or above this. Right. So this is 8. H is 8. This 8 equals 4 into mt. Mt 447 no, 477.5 into 10 power 3 divided by sigma b into length was 140 into diameter was 40. Right. Here. So we just need to find what is the crushing stress in this case, whether it is exceeding this or not, exceeding our value of 130 or not. So hopefully it doesn't. So 4 into 477.5 3 divided by 140 into 40 into 8. Yeah, you're right. It's 46.63 or 42.63 Newton per mm square. So this is again lesser than what the allowable stress is. That is 130 Newton per mm square. This is lesser than 130 newtons per mm square. So therefore, you can say that the design is safe. The design is safe. So whatever dimensions we have taken is according to the uh, data handbook, and it is correct. So these dimensions hold good. So that's how you are designing. So these dimensions, they take the stresses or torque, whatever is supplied to the system. So the length and dimensions, whatever is there. So now we are ready for that CAD design. So this is what engineers usually do. So they find out all the values, whether it is satisfying the given power requirements and given RPM and whatever material strength is there. So taking all these into account, you are deciding the dimensions. That is, diameter should be this much, then sleeve diameter should be this much, and length should be this. So these are all you are deciding. Okay. When you're a design engineer, you won't ask for dimensions. You'll ask what is the power, what is the speed you want, what is the maximum RPM, what is the displacement, all these things you'll ask for. And what you'll do is you'll fix the dimensions. You'll fix the dimensions like this. Once the dimensions are ready, you can directly go to CAD or any CAD software, and you can build the component, design the component, and export for drawing. So that's how companies do it. How they put the limits and all. So that's it. This is the first problem on this sleeve coupling. So all problems follow the same pattern. So there is no change in data we can give in this. So most of the things we have to mention power, or directly we have to give torque sometimes, and depending on power and speed and the limiting stresses, you'll just find the values. So that's how it usually flows. And we'll do just this one problem, because all problems on sleeve and muff coupling, they follow the same pattern. Okay, I'll send some additional problems you can practice at home. So, but all problems follow the same pattern. Okay. Then let's move on. Let's move on to the next type. So all 4 steps are done. So first problem we did. Okay. So this next topic is flange coupling. So flange coupling is another type of a rigid coupling, where you have to transmit power. So objective is to transmit the power between 2 shafts. So the shaft runs in the middle, and you can see this diameter d. The small d always represents the diameter of shaft. So we need to design the first diameter of shaft, and then we have also the keyway. So the key is the one which connects the flange to the shaft. So this entire thing rotates along with the shaft. Okay, that's how it is able to transmit power between 2 shafts. So you have 2 shafts which are broken, and then you fix it along with the flange coupling. And what all things you need to design here is the diameter of this inner diameter of the sleeve or flange, what we call outer diameter of the flange, then how many bolts in it. So these are called bolts, and this bolt circle. So where you need to position this bolt circle, that's called as a bolt circle diameter. So D1 is the bolt circle diameter, the pitch circle or the pitch circle diameter, bolt circle, or it is sometimes called bolt circle diameter, and how many number of bolts you need to put. So that is represented by I. Okay, and so I'll just write some few notation later on. Don't get confused. So I is the number of bolts. Number of bolts. Okay, so bolts will be usually fixed in this. So these are bolts. So usually bolts are standard diameter. We just need to decide what is the inner diameter, that is the tap diameter. We need to decide. Once we decide that, there is D1. Everything else follows the same. And here there is another two distinctions. T1 and T2 are there. So T1 is common for both. That is in flange coupling, we have two types. So we have one protected. Let me write here. This is protective, protected, and we have unprotected. Right. So we have two types here. So in unprotected, you won't have this. Okay, the bolts are protected here inside a casing. Unprotected, you won't have this much portion. Okay, it will be cut off from here. Okay, only T1 will not be there. Rest everything will be as usual. You will find T, which is the thickness of flange. Okay, both are identical. So you will not decide this separately and this separately. So it is both flanges are identical. What you decide is whether to write T1 or not. So in case of protected, you need to find both T and T1. So in case of unprotected, only T will be there. So there is no T1 and also there is no F. So very small differences between the protected and unprotected type of flange. And one more thing is this diameter, the inner diameter of the protected covering, inner diameter and this thickness F. So a few dimensions you have to decide in case of a protected type. So this will be usually given in the question. So what type of flange you need to design, whether protected or unprotected, and power requirements and everything will be same like the muff coupling, muff or sleeve coupling, what we did. So let's move on to the design procedure, how we design this particular flange coupling. So step one is as usual, you find the torque. Torque, you can use this equation or you can use 2 pi nt by 6. But here you keep the distinction. N is power, and this is in watts, and small n is speed, which is in RPM. But usually we won't use this. What general equation we have, we can use it. We can use this or that. Okay, only know the basic differences. Okay, like power equals to 2 pi nt, you can use by 60,000. So this is for torque. Okay, you can use this or this. Both are one and the same. Then step two is you find the diameter of shaft. So using this equation 19.2, you find what is the diameter of shaft. So once you find what is the diameter of shaft, all other dimensions will follow that that particular diameter. So that is step two. And usually here the torque will be given. The torque will begin, and nu is the keyway factor. I told you nu, the keyway factor usually taken as 0.75. So most commonly used value for keyway factor, that is nu. You can use that. And we have bolt circle diameter. That diameter we saw between the holes, right? So that is the bolt circle diameter. So this where there are a few bolts, and this diameter will be represented by D1. So this is important for designing purpose. You can't put the bolts wherever you want, right? Otherwise, stress concentration, then fatigue, all these things takes place. So therefore, this diameter has to be clearly known. So that's about bolt circle diameter. And also you can see it is dependent on the D, the diameter of shaft. The next step is designing of hub. So the hub is nothing but the flange itself, so which is covering the shaft. So that's the hub diameter D2, and what is the length or thickness of that particular hub, or this length also corresponds to length of the key. Right. Then finally design of flange. So the flange is the outer part, the outer diameter is denoted by D, and what is the thickness of flange. And once you find the dimensions, that is D and T, you need to check for flange. So check means whether whatever stresses is given, is it exceeding or not. So that is what check is about. So you modify this equation in terms of tau f, which is giving us the shear stress, whatever material is specified. So that shear stress it should not exceed. That's the bottom line. And once we find this, we just check it with the given data for stresses, shear stresses, and tell whether it is safe or not. That's step 5. So step 6, you decide the number of bolts. So as I told you, I is denoted by number of bolts, and also it is dependent on that diameter of shaft D. So once you find the number of bolts, you need to find the diameter of bolts. Okay, diameter, there is a small d1. So this is the core diameter. What kind of bolt you need to drill into it? What is the diameter? So depending on it, you check your bolts and nuts. So depending on this, you have to choose, and that's about step 6. This is supposed to be step 7. Six, right? 5. This is 6. Okay. This is 6. Oh, this is a continuation. Step 6 is you design the bolt, and again you have to check. Okay. Step 6 is to design this bolt and diameter of bolt, and continuation of the same step. You selecting from this table. This is a very big table, so that's why I'm not put it here. Once you select the diameter, the standard diameter of this, the size of bolt, then you check it for the diameter. You check for whatever values you have found. So sigma B is the stress, allowable stress, whichever is designed, and then depending on the material, you substitute all the values and find whether it is allowable or not. If not allowable, what you do is you change the diameter, increase the diameter by 1 count. By diameter, I mean the shaft diameter. Okay, so that's step 6. And 7. Step 7 is key. So this is the last step. So here, just like the previous Muff coupling, you find the, you would have already found, depending on diameter, you would have found B and H, and from L you would have got from the uh, sleeve itself, and you just find whether you check whether it is exceeding these stresses or not. So that's it about the steps. So totally there are 7 steps. So this is the lengthiest type of design which you encounter in DME, which has 7 different steps, and problems from this will vary for more than 20 marks. Okay, so I hope you learn this problem from step 1 to step 7. So this is usually the largest problem. So this is most common in exams and all. You might get this either in parts or in completely designing the flange bucket. So it will be for 20 marks. If it comes for the complete design, no, it will be for 20 marks full. Okay, so let's start off. Okay, so continuing with this, pump output 3000 liter per minute, total head 20. Head is the height at which it is pumping. Pump speed is 600. Efficiency 70%. Select C40 steel for shaft, that is 3 to 8.6 megapascal, and C35 steel, 304 MP. Usually metal properties will be given. So this is for bolts. Okay, check out. So this value is for bolts with factor of safety too. So once he mentions factor of safety, you are supposed to divide that for allowable stress. No, you should not use the same thing. And also, if he gives the yield stress, you can find the shear stress of that material. Okay. So this is yield stress for the shaft and yield stress for bolts. So with this, we can find what is the shear stress. If the need arises, we can find that. We use allowable shear stress for cast iron flanges. So this is also given. That is allowable shear stress for flange. Okay. So you have this much value. So let's write down the data first. So data, let's break it down first. So this is like let's say discharge Q. Q is the discharge or output. This will give us the quantity of how much volume of uh, liquid is coming out or water is coming out per minute or second. So usually we convert to seconds. We can use this data, right? So there is a Q in power transmitted. So there is one more equation which we can use to find the power transmitted. Okay, so Q is discharge, which is, let's say, 3000 liters per minute. So 3000 liters, which when you convert to meters, it will be 10 power minus 3 by 60. So this is in meter cube per second. So if you want to convert liters to meters, you divide by 1000, and minutes to seconds you can divide by 60. Okay, so that is one data. Then H is for head. We'll write capital H, which is the head, and that's given as 20 meters. And we have N as RPM. You can use N or N, small n sometimes. 600 RPM. So let's use small n. Let's use small n. Then efficiency. Efficiency is given in this time. So this is 70%. That is 0.7. We can keep that. And factor of safety. Factor of safety is 2. Okay, and also we need to write the yield stresses for each material. So yield stress sigma y equal to 328.6 newtons per mm squared for shaft. Okay, so this is important. We need to substitute those particular values whenever you are substituting or checking for stresses, right? And sigma y is 304 newtons per mm squared for bolts. So this is for bolts. And allowable shear stress tau. Allowable shear stress is 15 newtons per mm squared. This is for flange. Okay, so this much data you need to exclusively write it down. So let's see if I have missed anything from PowerPoint. Everything is there. Okay, so now let's start off. Step 1. So let's see go back to the PPT. Let's go to step 1. Okay, here. Step 1 is to find the torque transmitted. But torque transmitted here is not in the usual form. So it is given in terms of power. In terms of power, we know discharge and head. Okay, so this, let's see how we can find this. So instead, we need to find the power first, right? So let's see if we have any equation in the data handbook for that. Maybe somewhere here, if it is there, let's check. In terms of Q and H. Okay, we have torque, power, and power. We can use this equation. Something D. No, can't use this. So it should be in terms of Q and H. So wherever the Q, I think we can close in on our equation. No, we don't have it. In terms of power head, we don't have the equation. Okay, fine. So we'll take one equation which is here in the fluid mechanics. I think you've done this in during the fluid mechanics. So the formula goes like this. Let's say solution. Let's start off with the solution. This is step one. Step one is to find, according to the standard steps, to find the torque transmitted. So torque transmitted. So to find the torque transmitted, we don't have the power. So to find power, let's say P is equal to, also sometimes it is denoted as N, which is shown as rho Q G H by mu. So this is not in the data handbook. Okay, this is not in data handbook, and this is taken from fluid mechanics. Okay, FM. This formula I've taken from FM, which gives us power depending on pump uh, discharge and height, which is head. This is just acceleration due to gravity, and rho is just the density of the fluid. The fluid here, I think, is water, given in the question. So I'm guessing it is water. Not given, but I'm guessing it is water. So let's take it as water and try to solve this. That will be rho. So density for water is 1000 meter cube. Then this multiplied by this Q. Q is the discharge. Discharge was how much is this? 3000 power minus 3 divided by 60. This is giving us 0.05 meter cube per second. So use that here. So 0.05 still in meter cube into again 9.81, that is acceleration due to gravity, meter square per second by meter per second square. This is acceleration due to gravity into head is 20 meters. So everything is in meters, what I have substituted. So divided by the efficiency, pump efficiency, that is 0.7. So once we calculate this, since everything is in meters, we will get the unit of power in watts, kilowatts. In watts, not kilowatts. So N, or the power, is, I'm getting 14.01 kilowatts. So this is the power. So with this, once I get the power, I can use the general equation here. So I can use this equation, which is 2.87b, and I can take this value and find the torque transmitted. So MT is the torque transmitted, that is 9550 N by small n. This is equation 2.87p. You can directly substitute here. So 9550 into this power 14.01, let be in kilowatt, or convert to watts, 10 power 3, because it's in kilowatts, right? So divided by RPM, that is 600. That I think is given in data, 600 RPM. So torque will get by substituting this equation here. So 9550 into 14.0183 divided by 600. So that's coming around 2 to 3. Let me round it up. 2 to 3 into 10 power 3 Newton mm. Okay, so that's the torque. So usually this torque will be given, or even power will be given in the question. No? So, but this is a little bit twisted problem in terms of pump force and stuff. So usually it won't be this way. Usually torque or power will be directly given to you. You just need to substitute here and extract the value for torque. Right. So once the torque is known, let's move to next step. So step 2, according to the procedure, is to find the diameter of shaft. We're using the torque equation again. So let's see. So step 2 is diameter of shaft. So this is the base of everything, all the dimensions which we are going to design. So this dia of shaft is denoted by D. So it's given according to equation MT equal to, from that, let me just refer to that, pi D power pi into D cube. Then we have nu and tau by 60. So this is according to equation 19.2. Okay, there's some shuffling you have to do. That's it. So if we shuffle this, let's see what we get. We need D, that is the diameter. So then it will be cube root of 16 goes here. So therefore 16 MT divided by this tau. Tau I'll just subscript as D here, because that is with respect to the diameter into let's write into now itself, the efficiency or QA factor into that pi value. Right. So now we have everything, but we don't have tau D yet. So let's go back to the data. So we have, for shaft, we have only the yield stress. So from this, now we need to extract the tau D value. Okay, I'll just copy this first. Okay, so we have this value. Using this, so using this yield stress value, we need to extract the shear stress value. So shear stress is equal to, I told you before, to remember, this is 50% of yield stress divided by factor of safety. Okay, that's how we get the shear stress for anything. If yield stress is again 50% of that divided by factor of safety. So I think both of these data are given in the question, right? So this is 0.5 into what is yield stress is 328.5 0.6 divided by factor of safety. Factor of safety also was given. This is 2. So this is 2. Therefore, shear stress tau for the shaft will be different. 0.5 into 8.6 again divided by 2. So the shear stress is coming around 82.15 newtons per mm square. So let's substitute that value over here. So then we are supposed to get cube root of 16 into the torque. Torque, I think 2 to 3. Yeah? 2 to 3 into 10 power 3. 2 to 3 into 10 power 3 divided by tau d. So this is what tau d we about. Shear stress for the diameter is 82.15 into the efficiency was given, so 0.75 into 5. Okay. So once we solve for this, we'll get the diameter. So let's see you solve. I'll also solve in parallel. Let's find out what is the diameter. This is step 2. We got 16 into 2 to 3 E3 divided by 2.15 into 0.75 into 5. The cube root of that. So I'm getting an answer 26.42. Check if you got the same answer. I got 26.42 mm. So that's the diameter of shaft. This is actual, no rounded. It's not rounded, unrounded value of this diameter 26.42. But you need to refer to the data and look. Oh, I'm not pasting that. Just pull out that value from the hub. This is the diameter. I think I told you that list was too large to be used. So let's. This one. I think I showed you the standard values. Oh, it's here. This one. Here. Paste it here. Okay, so once we are done with step 2, we need to refer to this table 14.6. So from this standard diameters. So what value we got is 26.42. But see what we have the nearest value here. Nearest value 2530, so 30. So we have the nearest value itself as 30. So we can't round it off to 27 or 28. So you have to take 30. So that's according to the standard size of shaft, table 14.6. So referring to that table, 14.6. Refer table 14.6. So standard diameter D is 30 mm. Okay, so now this is very important because all other dimensions will be dependent on this sole diameter. Okay, if you make a smaller diameter or even the exact value, sometimes it won't satisfy the stress values. Okay, so be careful in taking this value. Always refer to the table and check with the diameter. Okay, so these are 2 steps done. I think 30% of the problem is done. So we'll continue this in the next class.